What do we remember about induction and inequalities from Pure Core 1? This is the example from Pure Core 1. However, the question is, the Pure Core 2 questions that use inequalities really rely on us having a good understanding of what was going on. So I'd quite like to look at it again as quickly as possible. So I'm now doing a new tactic with my pen where I hold it really low so that I don't accidentally press the buttons. So first of all, let's look at our base case. Oh, it's really working. Right, base case, n equals 5. So you can see that 2 to the 5 is 32. 6 times 5 plus 1 is 31. 32 is greater than 31. Therefore, it holds for n equals 5. Okay, it does look like I've done an identity there, but I've quickly recovered it. What we're now going to do is we're going to look at our inductive step. So we're going to assume that 2 to the k is greater than 6k plus 1. But importantly, that's for when k is greater than or equal to 5. So that's key to this question. So what I now need to do is, and a quick change of colour, I'm going to show that 2 to the k plus 1 is greater than 6 times k plus 1, i.e. 2 to the k plus 1 is greater than 6k plus 7. And what I'm going to do is I'm just going to cordon that off. Okay, I maybe went a little bit too much there with my loop. And if I could, I would move that. Oh, I can. Right, so that's what I'm now going to do. So let's do it. Oh, I've accidentally done it, held it too high. So here we go. 2 to the k plus 1, as you know, is 2 times 2 to the k. And we know that that means 2 to the k plus 1 will be greater than 2 times whatever 2 to the k is greater than. So that's going to be greater than 2 times 6k plus 1. So we know, oh, look, this is where I've done it before and had to start again. Right, so we're now going to have 2 to the k plus 1 is greater than 6k plus 2 plus another 6k. We know that if we expand this bracket, it'd be better if I had accelerated put that. You know that if I expand that bracket, I'm going to get 12k plus 2. And I've just chosen to write that here because it's easier to compare with the 6k plus 7. Now, we want to show that 2 to the k plus 1 is greater than 6k plus 7. So what we now need to do is show that 6k plus 2 is greater than 7. Now, because k is greater than or equal to 5, it has to be, doesn't it? 6k plus 2 is very definitely greater than 7, as k is greater than or equal to 5. In fact, it's going to be greater than or equal to 32. So because we've shown that, hence, we can see that 2 to the k plus 1 is indeed greater than 6 to the k plus 7, which is what we needed to show. And then our conclusion. So there's our conclusion. Inequality holds for our base case, assuming it holds for n equals k. We've shown it holds for n equals k plus 1, therefore, by the principle of mathematical induction, it will hold for all integers greater than or equal to 5. Right, example 2, so factorial. So factorial, again, this is from year 12 that you did with Miss Ennis. So I'd quickly like to look at it again. And I think the thing about the factorial examples, again, I need to remember to hold my pen is that n plus 1 factorial is n plus 1 times n factorial. Something, you know, obviously very familiar to you, but very important that we remember this. So the first thing we're going to look at is our base case. And again, this is when n equals 5. So we can see that 5 factorial we know is 120. We know that 20 times 5 is 100. 120 is greater than 100. Therefore, this holds for n equals 5. Right, our inductive step now. So 2. So we're going to assume that k factorial is greater than 20k, importantly for all integers where k is greater than or equal to 5. Now, what we need to show to prove this by induction is that k plus 1 factorial is greater than 20k plus 1, or k plus 1 factorial is greater than 20k plus 20. Okay, so I've cordoned that off that a little bit. So what I'm going to do is I'm going to rewrite my k plus 1 factorial. I'm going to do that over here. K plus 1 factorial we know is k plus 1 times k factorial. And that means we know that k plus 1 factorial will be greater than k plus 1 times whatever k factorial was greater than, which was 20k. So what we've got here is k plus 1 factorial is greater than 20k squared plus 20k. Now we want to show that this is greater than 20k plus 20. Well, we've got the 20k, so essentially you want to show that 20k squared is greater than 20. 20k squared is definitely going to be greater than 20 as long as k is greater than 1. And we know that k is greater than or equal to 5. So it's definitely greater than 20. So, therefore, k plus 1 factorial is indeed greater than what we were asked to show it, wasn't it? Is indeed greater than 20k plus 20. Because 20k squared is greater than 20. And here's our statement. Our conclusions. The statement is true for n equals 5. In fact, you'll see it's pretty much the same statement as we had last time. Okay, right, so that's a little recap of Year 12 work. And here we have some questions from Pure Core 1, Exercise 6C. Now, I think it would be good for you to try, or just, you may remember having done these before, so I think it would be good to have a go, definitely, at a couple of these factorial ones. So if you look at the syllabus, although these are in the Year 12 book, it seems to be that they're more on the A2 syllabus, but you will have done them in Year 12 with Miss Innes. So really good to have a recap, okay? And then we're going to see how this extends into Year 13. Thank you.